Hello, I'm Channa Bankapur. I'm going to discuss my solution to the LeetCode problem jump game third. It's today's daily challenge in LeetCode. The problem definition is we have an array of non-negative integers and a start position is given, which is an index of the array. When we are at some index I, we can either jump to I plus array of I or I minus of array of I. We can either go backwards or forward by array of I value, as long as the destination is within the array, right? And if I start this jump game, so starting from this start position, we need to figure out whether we can reach to a position where the value is zero, right? So that's all we need to do. And there are cases where you don't end up reaching to such a value. Let's try to understand this problem with an example here given. So the array is, I'm going to rewrite the array here. So the values are 4, 2, 3, uh, 0, 3, 1, 2, right? So these are the 7 values, and let me write the indices of them. So 0, 1, 2, 3, 4, 5, 6, right? So we are starting at position 5 here. That's what they have given. So we are going to start from here, and because it says 1, either we can go one position to the right or to the left. Both possibilities we need to explore. If I go to the left side here, it says 3, so we cannot go to the right because it's going to be beyond the array. So 4 plus 3 is going to be 7. 7 is not inside the array, but 4 minus 3 is going to be 1, so that is allowed, so we can go here. And at position 1 we have 2, so 1 minus 2 is minus 1, that is not allowed. That means we cannot go to the left side, but we can jump to the right side. 1 plus 2 is going to be 3, and we reached a destination. That means a value 0 is there, so that means we can return true for this problem. There are other paths, we didn't explore them, right? But what about the cases where we don't have such a solution? Suppose let me have everything similar except, say, at position 4 instead of 3 we have 4 here. So everything else is very similar, and we're going to start from position 5 itself. So when you start from position 5, either you can go to the left or to the right. So if I go to the left, it says 4, and the only choice is I can go to 4 minus 4 is 0, which is still allowed. And at 0, I cannot go to the left, but I can go to the right. So 0 plus 4 is 4. I came back here. That means this is not leading to anywhere better, so it's like a cycle. And if I go to in the beginning, if from position 5 to position 6, if I go from 6 to 4, we can go actually, and from 4 again we are stuck, right? We already figured out there is a cycle in that, and there is no way of reaching there. So in the second example, we should be returning false, right? So a very intuitive way of solving this problem is using a graph. So we can model this problem as a graph problem where every index or every node in this case, yeah, every index or every position is basically a node in the graph, a vertex in the graph. And every vertex has two possible edges. One goes to the left and one goes to the right in this case at the max. So in some cases, you don't have those edges also. So that's where we are going to that's how we can model it. And then there is already a start position given, so we need to figure out if there is a path from the start position to a node which has a value 0, right? So it's all about the reachability. So you can use any traversal algorithms like DFS traversal or BFS traversal, and see whether you can reach from start to a 0 node, right? Start node to a 0 node is all you need to figure out, right? But I'm going to solve it in a different way. So let me use recursive method, the way we solve dynamic programming problems. So the problem I'm solving is called F. So I'll start with the position here, right? Start is given to us. So I'm at this position at the moment. I have two possibilities. I can either go to the left or to the right. If I go to the left, so I'm going to be at a position called start plus array of start, right? So this is the position I am at. So now it's all about, now I need to see whether from this new position whether I can reach a 0 node. So that means it is the same problem F. So I'm going to solve for F of this, right? So this is going to return true or false, or I can go. So it is or, if any one of these two possibilities return true, I'm going to have a true value. So this another problem is F of start minus array of start, right? But we have seen already, so it's not like every time we have these two choices. Sometimes we don't have it. So these are conditional choices. the condition here is clearly this index should be within the array, right? So let me actually in the left side, I made a typo here. So it's going to be start minus array of start, and on the right side it is start plus array of start, because it is going to the left and it's going to the right. So this left side, it should not go below 0. So that means whatever we are writing here, start minus array of start, this should be greater than or equal to 0, right? If this condition is true, then only we solve this subproblem. On the right side, again, similarly, start plus array of start, if that is lesser than n, because n minus 1 is valid value. If it is lesser than n, then only it is valid. We can explore that possibility, right? So that's how we have already a recurrence here. So f of start, we have two possibilities which are conditional. If any one of them return true, we have a true as an answer. Now we need to figure out what are the base cases here. One clear base case is a true value. F of start is going to be true if array of start is 0, right? Because that is exactly what they've given. That's the only way to recognize a destination node. So whenever we reach there, we have an answer, and so it is true. But when do we return false? So just looking at a node, we don't have a way of figuring out it's a false. One false possible way is if there are two possibilities here, if both of them condition fail, that means we have a value at some position at start position. Whether you negate that from start or add that, both of them, if they go outside of the array, it's false. But that happens rarely, right? So there are other cases also. The other cases are cycles, right? So how do I identify a cycle? So when you are actually calling something like this recursively, so if you see if you reach to a node you already visited earlier in the same path, in the ancestral path, that means in the function stack, if it is still there, that means we are just doing it over and over, right? So that's how we need to figure it out. So it's not easy to put it in recurrence form here, but f of start is going to be false if start is already there in the stack, right? In stack as in the function stack, start is in the function stack, right? So let's see how to implement this. So identifying whether it's in the function stack or not is not that difficult. Whenever we call a function with a start value, we can remember we are in the stack for this particular start value, and every time you call a function, you can check whether we are in the stack. And when we are popping out, when we are returning from that function, you make sure you reset that to where we are in the stack. That means, yeah, you don't have to mark it as in the stack again, right? So this is the idea I'm going to use. So we already have recurrence and base cases. Let me directly implement it. Here, because the dependencies are totally dependent on the values in the array, making it bottom up is going to be hard here. So that's why I'm going to just implement the top down way. And it's very easy to see that there are overlapping subproblems here. So I'm going to use a DP method called Memoization, so that I'm still implementing the recursive version of this, but yeah, I'm going to remember the solutions I've solved for. So if I solve for say start equal to say 3, I'm not going to solve it again. So the only possible values are true and false. All right. So this is exactly what I'm trying to do. Let's see my code and try to see whether we understand it properly. Right. So in this public method, I have two tables initialized. One is the DP table, which is for memoization. So that's true or false, because we either there is either solution or no solution. If it is not in the map, so it's an unordered map. So if it is not inserted into the map, it is not yet solved. And again, whether we are in the stack or not for a particular index, we just need a set, because we just need to see whether we are in the stack or not. So we are going to insert when we get into that stack, and we are going to remove it or erase it when we come out of the stack. So this is the helper function I'm using, so which has the same array and start position. But yeah, we have these two tables, one for the DP memoization and one for identifying the cycles. So these are the base cases. The first base case is if start is already 0, that means we reach the destination and we are going to return true, right? Otherwise, if we are in the stack, so this like in stack, if count is not equal to 0, that means we are in the stack. In this case, we are getting into a cycle, so we're going to return false, right? And another one is if the problem is already solved. So if the problem is already solved, we are going to return whatever the solution it says, right? True or false. Now, from here, actually, we are processing apart from base cases. So here, I'm marking it as in stack for the start so that, I can identify if there's a cycle later. And again, I'm going to initialize the result to false. See, if both of these conditions are false, it's going to be false anyway, right? That's like a dead end. So false, and then if this condition is true, that means start minus array of start is greater than or equal to 0. Then only there is a possibility on the left side. So we're going to call with start minus array of start. Otherwise, in the other condition, I need to check for start plus array of start is less than n. Then only I call this function. Look at this. I'm having one more condition here. If not result, that means if the previous one already returns true, there is no point in exploring the other path, right? So we just need to be one of them needs to be true. So if one of them says true, I don't even evaluate the other one, right? So that's how I have a result. I'm going to update in the table and then take it out, take the start node out of the stack, and then return the result, right? So this is a simple memoization for the given recurrence. It should work, seamlessly. So let me submit and then show you, right? It's accepted, and let's see how much time it takes. Yep, this is pretty fast. 98 percentile means it is pretty fast. Even memory wise, 27 MB is not too much. We are starting with something like 26 MB here, like, and 27. So pretty much everyone's solution is linear time, space here. So that's why space is also not that bad. All right, let's see. So let's try to analyze the time complexity here and space complexity here. So if you see what happens in this case, we have a memoization here, and the only problems we are solving are linear number of problems. There are n problems to solve. And because of memoization, we don't solve a problem multiple times. And that's why this should make linear number of calls to this function f, right? And assuming these unordered map and unordered set, the operations are all big of one operations, constant time operations. The whole thing works in big of n time, right? And space wise, it also, we need these two tables. Both of them are linear time, linear space. So big of n extra space we take for map and then set, and also for recursion, right? So all of them put together is still big of n. All right. So, and if you really want to see a stricter, so this big of n time is on the assumption that these unordered map and unordered map and unordered set are essentially hash tables. So the time complexity big of one is amortized complexity. If you want to really see the actual time complexity, the worst case time complexity, you may just use a vector instead of a map, so which looks like this. This also works in the similar way, just that I'm using a vector and I have some -1 value indicating it is not yet solved, and then I need true or false for the problem to be solved. So that's why I have three values, right? I'm using int here instead of bool because -1 for unsolved, 0 means false, and then 1 means true, right? So that's why I needed three values here instead of two values, right? Otherwise, int stack is very similar. I'm going to initialize everything to my false, and pretty much everything else is, the same code, right? So this way, at least we can easily see the time it takes and space it takes is both of them are linear. All right. So I'm more interested in if anyone has solved using DFS or BFS traversal, or if you have a different approach other than these two methods, let me know. Otherwise, please like the video and subscribe to the channel and keep solving a problem every day. Thanks for watching.